I'm going to prove Liouville's theorem. Every bounded entire function f of z is constant. By the way, hello. An entire function means that it's holomorphic everywhere. If it's bounded, that means that the modulus of f of z is less than or equal to m for some real number m for all z belonging to the complex plane. And prove it's constant. In particular, I'm going to prove that f prime of w is equal to 0 for all w belonging to the complex plane. And the way I'm going to do that is I'm going to take the modulus of it, which is equal to the modulus of, this is equal to 1 over 2 pi I times the integral of f of z over z minus w squared over a circle CR. So here's what the picture looks like. The picture looks like take a w anywhere you like, and I'm going to draw a circle of radius r, and I can make that circle as big as I want. The reason why is because the function's entire. So the numerator here is going to be entire over, is going to be holomorphic over any of these circles, and the denominator is not going to be holomorphic because, of course, z minus w, if you plug in w, you're going to be divided by 0. So this is my strategy. I'm going to calculate this. I should have a dz in there. And I'm going to do this by, once again, maybe I can write this as 1 over 2 pi I times the integral of CR f of z minus w squared dz. Okay, and this 1 over 2 pi I, this is 1 over 2 pi times, to figure out the modulus of an integral, we're going to use the old trick if I'm just going to multiply by the length of the arc times the biggest value. And so just off to the side here, back in calculus, I don't know, if we want to integrate x squared from negative 1 to, say, I don't know, 2, that looks roughly like this. This is going to be less than or equal to the biggest possible value anywhere, which happens to be 4, times the length from negative 1 to 2, which is 3. So the biggest value times the length is how you do this. We're going to do the exact same process here. I'm going to estimate this by doing the biggest value of the integrand anywhere, just like I did the biggest value of x squared, times the length. So I'm going to write this as the maximum value times the length. But I know what the length is. This is just a circle of radius r, so this is just 2 pi r. The max part is a little trickier. So if I take the maximum of z minus w squared, oh, wait a second. This is a circle. Wait, well, before I have that revelation, let's just split this up into modulus of the numerator over modulus of the denominator, like so. But z minus w, the only points here integrating over are on the circle. And the circle is defined to be r units away from w, so this is equal to r squared. And the modulus of f, we know that this is bounded by m. That's one of the big hypotheses of the theorem, is that f is bounded. So I can replace this with m over r squared. And then I can simplify this. This is equal to, oh, this should be less than or equal to. Less than or equal to, because I'm doing an estimation. So that's 1 over 2 pi. Let's just set aside the scratch work, coordinate it off. 1 over 2 pi times m over r squared, that's constant, times 2 pi r, I'm just rewriting what I had. And I can simplify this down to, oh, cancel, m over r. So the derivative, f prime of w, is less than or equal to, m is bound, which is just some fixed number, it doesn't change, over r, which r happened to be the radius of the circle that we chose. But the key point here is that f is entire. So no matter how big I make the circle, this is going to be true for every single r belonging to r. Well, can anyone think of a number, a positive number, that's less than or equal to m over